These events are independent. Before I talked about the addition rule for probabilities, and now I'm going to talk about the multiplication rule. Remember that probability is about determining the likelihood of events. Now, first of all, I want to talk about independence of events. Independence of events, well, two events are independent if they do not affect one another. Like, for example, rolling a 5 and then rolling a 3 with a normal 6-sided die. These events are independent because rolling a 5 does not change the probability of rolling a 3. It's still going to be 1 out of 6. And the same is true the other way around. Like, rolling a 3 will not change the probability of rolling a 5. Now, two events are dependent if they do affect one another. Like, for example, drawing a king and then drawing a queen from a deck of cards without putting the king back. These events are dependent because drawing the king will change the probability of drawing a queen. Without the king in the deck, the probability of drawing a queen changes from 4 out of 52 to 4 out of 51. Basically, taking one card out of the deck changes the probability of another event because there are now less cards in the deck, which is why these are dependent events, because the presence of one event affects the probability of another. So what is the probability of rolling a 5 and then a 3 with a normal 6-sided die? Well, to answer this question, we have the multiplication rule for independent events, which is the probability of both A and B occurring is the probability of A times the probability of B. So the probability of getting a 3 and then a 5 is the probability of 3, which is 1 out of 6, times the probability of getting a 5, which is 1 out of 6. So the probability of getting both a 3 and then a 5 is 1 out of 36. And that is the multiplication rule for independent events.
Probability is what happens when you do a probability experiment more than once. Okay? Let's take a look at that in an example. Okay, so let's start with our candy beans over here. And let's put them in a sack. Shake it up really good. And let's do kind of a simple warm-up problem here to get you going. Let's find out what the probability is of drawing one green jelly bean. Okay, pretty simple. And remember, we have 3 green jelly beans here. 1, 2, 3. And let's check out that fun-to-use fraction we have. How many things will make you happy over total number of things? So in this case, 3 jelly beans would make us happy, and we have a total of 10 jelly beans. Nice and easy, that gives us a probability of 3 over 10, or 30%. Well, let's check out the type of problem we'll be looking at today. What is the probability now of drawing 2 green jelly beans in a row? Okay, so let's start thinking about this. And we'll begin with this question. How many times are you repeating this test, or how many trials are we having here? Well, since we're trying to draw 2 beans in a row, we have 2 separate trials. In the first trial, we have the bag with 10 beans, 3 green, and we're going to have the same bag? Oh boy, that doesn't, well, does that make sense? Let's think about this. So in trial 1, we've got these 10 beans in the bag here, and we're going to remove 1. Hopefully it's green. And then when we start our second trial, we're actually going to be starting with that very same bag. We're not going to have a fresh bag to begin with. We're going to be using the same one. And now the situation has changed. If you can tell, there's only 2 green jelly beans now, and we have a total of 9 jelly beans. So our fraction is going to change. The situation has changed there in our 2 different trials. So in our first trial, we have the full bag with 10 beans and 3 green ones. But after we remove one of those beans, we'll only have 2 green beans and a total of 9.
Wait. Excuse me, hold up a minute, sir.
Yeah, Joe, what's going on?
Do you remember how you said that on the first draw we took out a green bean?
Yeah, Joe.
Well, how do we know that we picked a green in the first trial?
Joe, that's actually a really good question. When we calculate compound probability, we always assume that the trials were successful, because that's what we're looking for, is what would happen if we did it correctly 2 times in a row. We could calculate it, the probability of not getting a green, but that's a different problem, maybe for a different video. But just remember, when you're calculating compound probability, you assume that the trials are successful. So in the first trial, we have 3 green beans, a 3 out of 10 chance. And on the second trial, one of those beans is already left, so we have a 2 out of 9 chance. So what exactly does that mean? Well, let's take a look at a simpler example and see how it lines up. Ah, our favorite pastime, flipping quarters and calculating the probabilities. Well, in this case, we're going to be flipping this quarter twice. So on our first flip, we have 2 possible outcomes, getting a heads or getting a tails. And if we had gotten a heads on our first trial, we have 2 possible outcomes of getting a heads again or getting a tails. And had we gotten a tails on the first trial, we have the possibilities of getting either a heads or a second tails. So actually, when we look at it, there are 4 possible outcomes for these experiments. Let's take a look at them in another way that's maybe a bit easier to understand. So if we put the results in a chart, we can see that we have one possibility of getting 2 heads in a row, a second possibility of getting 1 heads and then a tails, a third possibility of getting a tails and then a heads, and then finally a fourth possibility of getting 2 tails in the row. So if we do an experiment by flipping a coin twice, there are 4 possible outcomes. So if we're focusing on possibility 1, getting 2 heads in a row, we have a 1/4 chance of getting that, and that's as likely as any of the other possible outcomes. Let's take a look at the numbers behind there and see if we can figure out how to get 1/4. Well, if we're trying to get 2 heads in the row, that means we need to get a heads on the first trial, which is a 1/2 chance. We also have a 1/2 chance of not getting a heads, getting a tails. But right now we're focusing on getting a heads. Okay, we have a 1/2 chance of getting a heads in the first trial and a 1/2 chance of getting a heads in the second trial. So that gives us these 2 probabilities here, 1/2 and 1/2. And how do we relate those 2 numbers together to get a 1/4? I think you've gotten it right. We're going to multiply. And if we multiply 1/2 times 1/2, we get 1/4. So that's what we do with our probabilities here. If we know we have a 3 out of 10 chance on the first trial and a 2 out of 9 chance on the second trial, we can simply multiply those 2 probabilities together. We get 6 out of 90 or 1 out of 15. Okay, which is a pretty small chance. Think about that. If you had 10 beans in a bag and you were trying to get 2 from a pile of 3 within that bag of 10, there'd be a very small chance of getting those at random. You're much more likely to get a red or a yellow in there by accident. Okay, let's take a look at another example. Pretend that you and your friend are at the fair and they're having a raffle, and in fact, you notice that there's not very many tickets in the drum there, and you and your friend both enter. There's 8 total tickets, 2 of which one belongs to your friend and 1 belongs to you, and they're actually doing 2 drawings in a row here. And we want to know what is the probability of both you and your friend winning. First question we want to ask is, how many times are we repeating this test, or how many trials do we have here? In this case, since there's 2 drawings, we're going to have 2 trials. Let's take a look. Trial 1, we have all 8 tickets. Both you and your friends are still there. So that gives us a 2, because there's 2 tickets. That'll make us happy, out of an 8 total amount of tickets. And once one of those tickets is removed, because we're assuming that the trial was successful, 7 total tickets now, and one of those, which is a winner for us. So now we have 2 fractions, 2 over 8, 1 over 7. We'll go ahead and combine them. So 2 over 8 times 1 over 7 gives you 2 over 56, or 1 over 28. Still pretty rare odds of both you and your friends winning in a even such a small raffle. Try the calculation with 800 total tickets, and you'll see what I mean. Okay, let's take a look at this example here. I'm sure you're all familiar with spinners. And the question we're going to ask today is, what is the probability of spinning a number greater than 4 twice in a row? Okay. So we actually have 2 numbers here that are greater than 4. We have 5 and we have 6. And since we're going to be spinning the spinner twice, we have 2 trials. So on spinner 1, I'm going to spin the spinner and hypothetically land on either 5 or 6. One of those will be removed. And we'll get over to trial 2 and we'll spin. And now, since there's only 1 that will make us happy out of 5 total wedges, we'll take those 2 numbers and multiply them together. Wait a minute. Does this make sense? Is that the way a spinner works? When you spin a spinner and it lands on a number, do you lose that option for the next round? No, actually. No matter how many times I spin a spinner, I'm always going to have the same number of possible outcomes. And if I'm looking for specific results, I'm always going to have that same amount of specific results. Remember, no matter how many times you spin a spinner or roll a dice or flip a coin, it will always have the same number of possible outcomes. So what's the difference here? On the left hand, we've got these spinners that don't ever change no matter how many times we repeat the experiment. And then we have something like a bag of jelly beans on the right-hand side that does change every time we do an experiment. In fact, might drastically change depending on how many times we do an experiment. Well, those two things are called events, and we can define them as being either independent or dependent. Independent events are when the outcome of the event does not influence the outcome of a second event. So again, flipping a coin, spinning a spinner, rolling a dice. No matter how many times we repeat those experiments, the situation is always going to be the same. However, with dependent events, the outcome of one event does influence the second event. So for example, drawing cards or picking from a bag. And that only works when drawn items are not returned. So a question you'll want to ask yourself when solving for compound probability is, does it depend what happens the first time? If the answer is no, then the events are independent. If the answer is yes, then the events are dependent. It depends what happens. So let's go back to our spinner problem. The spinner used in the second trial is exactly the same as the spinner used in the first trial. No matter how many times you spin it, it will always have the same number of outcomes. That 2 wedges greater than the number 4 out of 6 total wedges is the same probability we have for the second trial. So, as you'd probably expect, we take the 2 fractions and we multiply them together. And this would be true if we did 3 trials, 5 trials, or 100 trials. 2 over 6 times 2 over 6 gives us 4 over 36, which we can reduce to 1 over 9. Oh, wow. Looks like we've got another one of these stretch it questions. Well, okay, let's take a look at it. That gentleman you're seeing in front of you there, that young man there, is Bobby Fischer. And Bobby Fischer is well known for being one of the finest chess players ever in the history. Some say he's the greatest ever. And when young Bobby Fischer was just 14 years old, he was in the finals of actually 8 different U.S. championship chess matches. He got into the final round of 8 different ones. And we want to calculate here, what is the probability that Bobby wins all 8 of those matches? So we have probably a 1/2 chance of winning because he's just got to play 1 round against 1 guy. So he's either the winner or he's not. And I guess we could take all those numbers and multiply them together, and that gives us 1 over 256. A very small chance. No, I hope you guys picked up on that there. Actually, we wouldn't do that because, believe it or not, Fischer, the guy there on the left there with the big grin, was actually a genius and an expert in chess. In fact, he, at 14 years old, won all 8 of those championships. Because remember, chess is not a game of random chance. It's a game of skill. And probability only works for random games of chance, not for games of skill or ability.
Now let's look at a mutually exclusive event. So mutually exclusive events cannot happen at the same time. Impossible. So what that means is that the probability of A and B occurring is 0, because they cannot happen at the same time. Now this we're going to use for later. Okay, but we could have an or there. So it is or possible. Now let's think of our dice. Now, what would be the probability of rolling a 4 and a 2? Well, I can't roll a 4 and a 2. It's not physically possible for the dice to go down and land so to be exactly a 4 or a 2. It could be a 4 or a 2 or something else. So this is a mutually exclusive event, so that probability is 0. But we bring up the special idea of or, and this is where we get our special rule of addition. Because and really limits us, but or gives us options. And this is where we're going to say the probability of A or B is equal to the probability of A plus the probability of B. So let's change it now to fit the probability of rolling a 4 or a 2. Now that's possible. Or means it's either a 4 or a 2. This means I can break it up to the probability of a 4 plus the probability of a 2. Now, 6-sided dice, I have 1/6 plus 1/6. I get 2/6 or a 1/3 probability. I roll a 4 or a 2. Now, if we were thinking about cards, the probability, if I pulled a single card, that it would be a ace and a face card is 0. I cannot physically pull both of those. It won't happen. But I could look at the probability I pull an ace or a face card, which means a different thing. So ace or a face card becomes the probability of an ace plus the probability of a face card. Now, the probability of an ace, there are 4 aces in a deck, and face cards, jack, queen, king, there are 12. There's 3 in each suit, and there's 4 suits. So combining those together, I get 16 in 52, which is 4/13. So that is the probability I get an ace or a face card. Now, we may see it in terms of cards or dice, but we also may start to see it in decimal form. So let's say I had a mutually exclusive event where the probability of A was 0.6 and the probability of B was 0.25. So the probability in this case of A and B occurring. Now, the values here don't tell me this answer. This comes down to knowing the rule, which we stated right here. The probability of A and B happening is 0. They can't both happen at the same time. Now, the probability of A or B occurring, though, is different. This is our rule here, where I can add them together, and I get 0.6 plus 0.25, which gives me 0.85. So the or here is actually 0.85, or 85%. Now, let's also throw in, what if I wanted the probability of not A or B? So this is the complement of this value. So that's going to be 1 minus 0.85, which comes out to 0.15, or 15%. Remember, these two have to add up to 1. So those are mutually exclusive events. The and is 0, the or, we combine the probabilities. The next one we have to look at is independent events. And this is where the first event does not affect the second event. So we could have them both occur. And we also may see these referred to as overlapping. Now in this case, the and is possible. So and the probability of those occurring is the probability of A times the probability of B. Now this is the big difference to start off with between mutually exclusive. In mutually exclusive, the ands is a 0. Here, we're going to multiply the two probabilities. Now, because there is an overlap, we also have to change our general rule for addition that we had. So the rule of addition now becomes the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, which I'm going to try to show you in some examples. So let's say we are pulling some cards from a deck of cards, and I'm looking at the probability I pull a 7. Now there are 4 7s out of 52, and if I even write the sample space of this, I have a 7 of diamonds, a 7 of hearts, a 7 of clubs, and a 7 of spades. Then if I'm looking at the probability that I pull a diamond, there are 13 out of 52 diamonds. And that starts at ace, and goes all the way to king. 13 of those. So let's start with looking at the probability that I pull a 7 and a diamond. So in this case, I pull a card, and if I pull a 7 or I pull a diamond, it really doesn't affect it. It's just something they may have in common, which it is possible, and that's actually the same as pulling the probability of a 7 of diamonds, because there is that card. So using the rule right here, I want to find the probability of a 7 times the probability of a diamond, which I have already done, which I have 4 over 52 times 13 over 52. I've reduced them, and this comes out to be, I reduce them correctly would help. This comes out to be 1 over 52. So there's a 1 in 52 chance that I would pull a 7 and a diamond, or the 7 of diamonds, which should make sense. There's only one of them. Now, let's go to the or statement. So this is the probability of a 7 or a diamond. Now, if I just did the probability of a 7 plus the probability of a diamond, let's look at that scenario. So there are 4 out of 52 are 7s, and 13 out of 52 are diamonds. And if I look at this group and I count them, I actually get 17 total. But 17 over 52 is not our correct answer. And the issue is this right here. This card, or these values right here, are the exact same card. This is the 7 of hearts. Try again. These two are the 7 of diamonds. They are the exact same. This shows up in both of them. This is an overlap. And the issue is, if I count 4 and 13 and stay 17, I'm actually counting this one twice. So this is where, in our rule up here, we have to subtract the and. And the and is 1 in 52. So now I get 16 over 52, which comes out to be 4/13. So you got to be careful on these and paying attention to that overlap. They don't want to double count, and that's what an overlap does. Now, let's say I have a couple others with independent events. Independent events C and D, where I know the probability of C is 0.55, the probability of D, 0.4, and the probability of C and D, 0.22. So I'm going to first figure out the probability that C or D occurs. So here it's going to be the probability of C plus the probability of D minus the overlap. That's what we get from our addition rule. That's C and D. When we think of or, remember it could be both. That's why we got to subtract an overlap. Now, if you accidentally put this when there was no overlap, it would just be 0 and it wouldn't affect it, but it's good habit to put that there. So I got 0.55 plus 0.40 minus 0.22. 0.95 minus 0.22, and I get 73 hundredths, or 73%. Now, let's check the probability of not C or D. So in this case, I'm now going to do 1 minus the probability of C or D, which is going to be 1 minus 0.73, or 100% minus 73%, which gives us 0.27. Okay, well, what if I had independent events E and F? And now this time, what I know about E and F is that the probability of E is 0.75, and the probability of F is 0.2. So if I'm going to figure out the probability of E or F, I first have to do a little bit of work, because I know this is the probability of E plus the probability of F minus the probability of E and F. But I don't know this yet. So the way I figure this out is by saying the probability of E and F is equal to the probability of E times the probability of F, which is 0.75 times 0.2. So we get that's 15 hundredths or 15%. So now I can put these all together and I get 0.75 plus 0.2, 0, we'll throw a 0 on there, minus 0.15. This is 95 hundredths minus 15 hundredths, we get 0.80 or 80%. And for our last example, we're going to look at this two-way table where we're comparing cars, trucks, and vans, as well as white, blue, silver, and black colors out of 500, let's say cars or vehicles in the parking lot. So let's start working our way through some of these. So if I started with the probability that I would pick a car out of all of these in the lot, and that's saying I'm looking at this column, and there are 125 out of 500 cars. And that reduces to be 1/4. If I then said, well, what about the probability I have a white car? You know, a white car, or a white vehicle, I should say. Probability it's white. I'm going to add up all of this column, and I get 225 over 500. And this becomes 9 over 20. Now, let's start putting these together. What if I said the probability it's a car and it's white? Now, if it's a car and white, it has to meet both conditions. So it has to be in this column, and it has to be in this row. And there's only one that does that, and that's the 100 right here. So this is going to be 100. So this is going to be 100 over 500, or 1/5. So it's car and white. Now, that's different than if it was car or white. Now, by these being independent events, because it really doesn't matter if a car is white, or if car is the vehicle or that it's white, we're going to use the probability it's a car plus the probability it's white minus the probability it's a car and it's white. And we can see this by looking here, because if I just took the cars column and added up these numbers, 100, 15, 5, and 5, I get the total for the cars. If I took the white, 100, 75, 50, and got 225, I double counted this 100. I don't want to do that. I actually just want each of these values once. So by subtracting the overlap, or that 100, it's going to give me an accurate value. So the probability of the cars was 125 over 500, plus the probability it's white was 225 over 500, minus 100 over 500. Now I get 125 plus 225 is 350, minus 100, it turns out to be 250 over 500, or 1/2. Now, let's think we had the probability that we picked a silver vehicle and a black vehicle. Silver and black, these actually cannot happen at the same time. Silver is here, black is here, and there's nothing overlapping, so they can't occur there. These are going to be mutually exclusive, so we make that at 0. But that doesn't mean it's impossible, because what if we said silver or black? So silver or black, it could be in this column, and it could be in this column, and they're independent because they could both happen. So I'm going to do the probability of silver plus the probability it's black, and I'm going to subtract the probability it's silver and black. But we've already said that's 0, but it's worth paying attention to. Maybe that does show up. It's good to be careful as we do that. So silver is 75 over 500. Black is 140 over 500 minus 0 over 500, and we get 215 over 500. Okay, well, what if we said the probability it's black and a truck? So black and a truck, that means it has to be in the black and it has to be truck. So the only thing that has in common here in the and is the 100. So that's going to be 100 out of 500 or 1/5. How about the probability? How about the probability it's not a truck? So I could take the probability of it being a truck and subtract it from 1, or I can look at the options. So let's see this. If this is the truck, I could take 240 1 minus 240 over 500, which is, this is just 500 over 500, and I get 260 over 500, which becomes 260 over 500, ultimately 26 over 50, or 13 over 25. Now, one last one we'll look at is the probability that it's not a van and it's black. So probability it's not a van and it's black. So I'm going to first find this probability, because the probability of not a van is going to be important. So a van is this column. So that's 135 out of the 500. That leaves 365 left over. But that has to be black. So it's actually these right here. And what we could start to do when we get more specific is you can eliminate this column and you can eliminate the others. So it has to be that 105 over 500. Which would be 21 over 100. And as you start to do these, you'll start to just eliminate them, because really it's not being not a van, it's the fact it's a car and a truck, and it has to be black. So which of those would also work?
Let's pretend that you have 16 marbles, and 5 of them are red and 11 of them are blue. And someone asks you, what is the probability of picking first a blue one and then a red one? At first glance, you'd be tempted to say, hey, this is easy. I remember from the last video, a probability is how many ways there is to do something over the total number of ways. So how many ways are there to pick a blue marble from this bucket of 16 marbles? And you say, well, there's 11 of them, so 11 out of 16. And similarly, you would say, well, for the red ones, there are 5 red ones in there, and there's 16, so it's got to be 5 out of 16. But it is, of course, not that easy, and let's actually do it so we can see why that's the case. So first, you are asked to pull out a marble, and you do, and it's blue, and how many ways were there to do that? Well, there were 11 out of 16. Now, what about the red marble? Well, there's 5 out of 16, but no, there really isn't. Remember, we removed a marble, so now there's only 15 marbles left, so it would be 5 out of 15. So what happened here? Well, we did not put this marble back in the pot. We did not replace it. And so these are not really independent events, because the probability of this one depends on what happened before it, right? If we had pulled out a red marble initially, then it wouldn't be 5 out of 15. There would be 4 red marbles left in a pot of 15 marbles. It'd be 4 out of 15. So it's not independent. If this is a little complicated, don't worry about it. I'm just showing this to you so you can kind of get an understanding that sometimes one probability can depend on the other, but we're not going to look at those. We're only going to look at independent events. So let's put this blue marble back, and let's try this another way. So we'll ask the same question again. What is the probability of getting a blue one first, and then a red one? So you're going to take a marble out. And how many ways were there to get that blue marble? Well, we knew there were 11 to start with out of a total of 16, so it is 11 out of 16. Now, what's different than the previous example is we're going to put this marble back. We're going to replace it. And now look, we have a pot again of 16 marbles, 5 of which are red and 11 of which are blue. Now, how many ways are there to get a red out of there? 5, 1, 2, 3, 4, 5 out of 16. So we took a red one out of the pot of 16, 5 out of 16. So here we did have a replacement. And because we did put that first marble back in the pot, we returned it back to its initial state. The second marble draw had nothing to do with the first one because this one and this one were drawn from the exact same pool of marbles. So they are independent of each other. This one does not depend on what was drawn first. Okay, all that said, we are not going to deal with non-independent events now. We're just going to deal with independent events. So now let's talk about the multiplication rule. And what that does is it means that if you want to ask what is the probability of something happening and something else happening, you just take the probabilities of each one of those things and you multiply them. That's why we say and that's why it's called the multiplication rule. So the probability of picking a blue one and then picking a red one is going to be the probability of picking a blue one multiplied by the probability of picking a red one. So that's 11/16 times 5/16, and that comes out to 55 over 256, or 0.21, or 21%. So that's the and rule, the multiplication rule. If you want to know what the probability of one thing and something else happening is, and they are independent events, that is, they don't depend on each other, then you multiply them. So in this case where we did not have replacement, we can't use that rule, but we're only going to be talking about independent events here. Okay, now let's look at the addition rule. So in this previous example, what I had asked was, what is the probability of getting a blue one and then getting a red one? Now what I'm going to ask is, what is the probability of getting a blue and a red in any order? Initially I said you had to first get a blue and then a red. Now I'm saying get a blue and a red in any order. So there's really only two ways you could do this. And we're going to do it with replacement. So you can either draw a blue first, then a red, or you can get a red first and then a blue. So what is the probability of getting a blue marble? It's 11 out of 16. What is the probability of getting a red one? It's 5 out of 16. Now, as you guessed, this or is going to mean that we're going to add the probabilities. And so we have two things going on here. We're using both rules, multiplication and addition. We're saying you can either get a blue and a red, or a red and a blue. So this mathematically would translate to getting a blue and a red, so there's a multiplication happening here, or getting a red and a blue with a multiplication happening here. And in between, we have that addition. And this probability would be about 43%, 110 over 256, or 0.428. And I know you're thinking, marbles are great and all, but what does this have to do with anything? Well, we do use probability a lot. We're going to be using it throughout evidence-based medicine, but let me show you how we're going to use it in genetics. So say we have two parents, a mom and a dad, and they want to have children, but they're afraid that there's a disease that runs in their family. So they ask you about it. Is our kid going to get this whenever we decide to have a kid? What's the probability of that happening? And so the parents undergo genetic testing, and they get the following results. They are both carriers. They both have one healthy allele for that gene, and they have one disease allele for that gene. So if they have kids, we don't know which gene from mom the kids are going to get, or which the gene from dad the kids are going to get. So let's figure out what all the possibilities are. And here they are. They can either both get the kid can either get two healthy alleles, could get one healthy one and one not healthy one, or both unhealthy ones. And let's say for this disease, it's a recessive disease. So if they are unlucky to get both, then that kid is going to develop the disease. So what are the ways that a kid will be born and will be healthy? Well, they can either have two of the healthy alleles, or they could have one healthy allele and one unhealthy allele. So what's the probability of getting this? Well, if we look over here, it's 1 out of 4. And what's the probability of getting one of each, being heterozygous? You can have this one or this one, so it's 2 out of 4. And so, since we said this was an or situation, we're going to be using our addition rule, and so if we add these numbers up, we get 3 out of 4. And if we look at this, that was obvious, pretty obvious, because we have 1, 2, 3 ways to be healthy out of a total of 4.